Very nice welcome to Indian farmer, Awarthian Krishak and Bhartiya Hindustani Kishan. Quantum 6 class. And the previous we study about the uh, Schrodinger equation that's Schrodinger said that made a bold extrapolation that and postulated that the form of equation previously that is Schrodinger equation does not change even for a particle of mass m moving in a potential which varies with x and time. Thus, the time-dependent Schrodinger equation for a one-dimensional motion of a particle of mass m moving in a potential Vx comma t is given by I h cut del psi by del t equals to minus h cut square by 2m into del 2 psi by del x square plus Vx comma t psi x comma t. This is equation 9 which represents Schrodinger equation, and this is the second postulate of quantum physics known as time evolution of a system. The appearance of H cut in the Schrodinger equation is of course crucial. This is how Schrodinger imposed the quantum condition on the wave equation of matter. The Schrodinger equation is unlike any of the wave equations we have come across so far. Recall that wave equations usually connect a second order time derivatives of the function with its second order spatial derivative. Schrodinger equation contains only the first derivative with respect to time but the second derivative with respect to a space. Hence, time and space coordinates are not treated on an equal footing in this equation. So, equation 9 cannot be correct in the relativistic domain. Hence, it is a non-relativistic time-dependent Schrodinger equation. And it is a price to pay for having only a first order time derivative in the wave equation. The solution of the Schrodinger equation are not real physical waves. They are complex functions with both a real and an imaginary part. This gives rise to the problem of interpretation of the wave function. So, what exactly does the wave function psi x comma t mean physically? So, we will discuss the interpretation of psi given by Max Born, and it is also known as a statistical interpretation of the wave function. The coefficient of the time derivative of psi in Schrodinger equation is imaginary in above equation. Therefore, it is evident that the wave function psi, which is the solution of equation 9, uh, will in general be complex. Thus, in order to extract any physical information from psi x comma t, we must establish a quantitative connection between psi x comma t and the observables of the particle. In 1926, Max Born proposed the following connection. If at any time t, a measurement is made to locate the object represented by the wave function psi x comma t, then the probability px comma t dx that the object will be found between the coordinate x and x plus dx is px comma t dx equals to psi strict x comma t psi x comma t dx equals to a square of modulus psi x comma t dx. This is equation 10. This is equation where asterisk on a function represents its complex conjugate. So we can see that a square of modulus psi xt is the modulus square of the wave function. Here px comma t dx psi stick psi x comma t equals to a square of modulus psi x comma t is also termed as probability density. To put it in words, the probability density, the probability of finding a quantum mechanical object in a small interval dx is given by the product of modulus square of the wave function representing the object and the interval itself. So the probability of finding the particle within some finite length L equals to x2 minus x1 is given by PL t equals to integration x1 to x2 p x comma t dx. And we know that px comma t is equal to the psi stick x comma t into psi x comma t. Thus, according to Max Born, the Schrodinger equation gives probability waves. The wave function just tells us probabilistically where the likelihood of finding the particle will be greater. There the wave will be strong, its amplitude will be larger. If the probability of finding a particle in a region is small, the wave will be weak and its amplitude will be small. It may seem from the above probabilistic interpretation that the phase of the wave function is not important, since it is a modulus square of psi x comma t that we interpret as the probability. And the above postulate is that is known as this postulate. This is third postulate of quantum mechanics, as known as probabilistic interpretation of the wave function. So with this, I would like to end this lecture here. I think you have enjoyed this very much.